Morning to all students. We have already done carboxylic acids and substituted carboxylic acid in your previous semester. Now we will do carboxylic acid derivatives. The general formula of carboxylic acid is RCOOH. But when hydroxyl part of acid group of carboxylic acid is replaced by any other atom or group of atom like X, any halogen atom, RCOO group or RO group like alkoxy group and NH2 group respectively, we get functional derivatives of carboxylic acids or simply known as derivatives of carboxylic acids because they all give parent acids when we do hydrolysis of these acid derivatives. In this structure, it is very clear when hydroxyl group is replaced by X, we get acid chloride. So RCOX is the general formula of acid chloride where X can be chlorine, bromine or iodine. When this hydroxyl group is replaced by RCOO group, then get acid anhydride. When hydroxyl group is replaced by alkoxy group, we obtain ester, and when hydroxyl group is replaced by amide group, NH2 group, we get amides. In all these cases, R group and R dash may be same or different. So simple or substituted alkyl or aryl groups may be there. Further, since all these derivatives contain same acyl group in their structure, so they are also commonly known as acyl compounds. The next topic is electronic structure of acid derivatives. In acid derivatives, there is sp2 hybridized carbonyl carbon, which is doubly bonded to oxygen with one sigma bond and one pi bond, and it forms single bond with two monovalent groups R and L, and bond angle between these groups is approximately 120 degrees. Since the group L, chlorine in case of acid chloride, oxygen in case of anhydrides and esters, and N in case of amide, directly linked to carbonyl carbon, has minimum at least one lone pair, like one lone pair on the nitrogen, two lone pairs on the oxygens, and three lone pairs in case of chlorine present in acid chloride. In figure 7.1, it is very clear the lone pair present in the p orbital of L can sidewise overlap with p orbitals of carbon and further oxygen. So this provides additional bonding in this structure as shown here. So carbonyl compounds, these acid derivatives compounds have flat structure because of sp2 hybridization of carbon atoms. Next topic is nucleophilic acyl substitution. These acid derivatives have carbonyl group, so these compounds undergo nucleophilic substitution reactions. Because attacking reagent is nucleophile and overall reaction is substitution reaction, here L group is replaced by any other attacking reagent, nucleophilic reagent. So the reaction is known as substitution reaction, in which chlorine, ester group, or OR group, NH2 group is replaced by other nucleophile or basic group. Since this substitution occurs at acyl group, it is generally referred to as nucleophilic acyl substitution. So this acyl substitution is a different feature of these acid derivatives as compared to nucleophilic alkyl substitution in case of alkyl halides. The mechanism of this nucleophilic substitution reaction is shown here. In the first step, nucleophile, which is rich in electron, which has lone pair, attacks on the carbonyl carbon because this carbon has a delta positive charge as it is attached to more electronegative oxygen atom. So this nucleophile easily attacks on the carbon, then this pi electron of carbonyl group shift toward the oxygen and we get addition compound where nucleophile attached to carbon and oxygen gain a negative charge. And this sp2 hybridized carbon converts into sp3 hybridized carbon, means it converts into tetrahedral structure from the previous structure. After this addition or attack of nucleophile, there is rearrangement of electron. This lone pair from the oxygen means negative charge, which oxygen accommodated earlier, shift toward the carbon. So it again forms carbonyl bond and the leaving group leaves with its electron pair and we get final substituted product. And this nucleophilic substitution reaction in acid derivatives depends upon the two factors, steric hindrance and electron donating group. If there is steric hindrance around the carbon, means size of this R group affect the reactivity or attack of nucleophile. If there is steric hindrance, there are bulky group present around the carbon, then attack of nucleophile will be difficult on carbonyl carbon and it decreases the reactivity or decreases the nucleophilic substitution reaction, reactivity of these compounds toward nucleophilic substitution reaction. Second point is electron donating group. If there are electron donating group present on the carbon, then that groups try to increase negative charge on the oxygen, means they intensify the charge on this addition product on the oxygen. So it decreases the stability of this and further decreases the reactivity toward nucleophilic substitution reaction. Second is, in second step, leaving group leaves the carbonyl carbon. The nature of leaving group affect the reaction. Weaker the base, the better is leaving group, and we know chlorine is weak base, RCO negative is moderately strong base as compared to Cl negative. OR negative is strong base, NH2 negative is strongest base. In other words, we can say chloride is very good leaving group because it is weaker base, and NH2 negative is least bad leaving group because it is a very strong base. As here it is clear, weaker the base, better is the leaving group. So Cl negative easily leaves, it is more reactive as compared to other acid derivatives. If we compare these compounds with aldehydes and ketones, in case of aldehyde or ketone, there is R or hydrogen. When nucleophile attacks on the carbonyl carbon, the leaving group will be R dash or hydrogen. But this doesn't happen since R negative and H negative are the poorest leaving group. So And this is the difference of acid derivatives from aldehydes and ketones, because in case of aldehyde or ketone, it will involve removal of hydride or alkyl ion, which is not easily possible. So aldehydes and ketones do not undergo nucleophilic substitution reactions. From this discussion, it follows that acid derivatives undergo nucleophilic acyl substitution reaction, since the leaving groups are much better as compared to hydride and alkyl ions in case of aldehydes and ketones. The complete mechanism of this reaction is shown as: firstly, nucleophile attacks on the carbon. We can show this in this transition state, where the bond between nucleophile and carbon formation start, and pi bond between carbon and oxygen bond breaking start. Ultimately, there is full form, complete bond formation between nucleophile and carbon, and oxygen acquires negative charge. Then there is rearrangement of electron and leaving of R group, and finally we get a substituted product by nucleophilic addition reaction. Then next topic is relative stability of acid derivatives and their order of reactivity. As there is large difference in reactivity of various acid derivatives toward nucleophilic substitution reactions, it has been found experimentally the reactivity order is in this order. Acid chlorides are more reactive than acid anhydrides, then esters, and least reactives are acid amides. This order of reactivity mainly depends on the two factors: stability of resonance structure of acid derivative, and second is it also depends upon ability of the leaving groups to depart after attack of a nucleophile. Acid derivatives are shown by these resonance structures. In first structure, it is a normal structure, but oxygen is more reactive than carbon, so it can accept electron pair, it can attract electron towards itself. So by doing this, carbon may have positive charge, oxygen has a negative charge. Further, as this L group has lone pair, minimum one lone pair in each case, this electron pair undergo delocalization and we get a structure third. So in this structure, there is dispersal of positive charge from the carbonyl carbon. Structure 3 is very important toward the resonance hybrid of these acid derivatives. So greater the contribution of structure 3, greater is the stability of acid derivative. अगर stability greater है, then reactivity less होगी towards the nucleophilic acyl substitution reaction. Now we compare the stability of structure 3 in each case. Structure 3A shows this structure third of acid amides. Structure 3B shows the case of ester. Structure 3 shows the case of anhydride. Structure 3B shows case of acid chloride. So first of all, we will compare 3A with B and C. In structure 3A, in case of acid amide, there is nitrogen atom, and this nitrogen is less electronegative than oxygen of ester and anhydride. So it can easily donate its lone pair toward the contribution of this resonance structure. So structure 3A is more stable as compared to 3B and 3C because of the less electronegativity of nitrogen as compared to oxygen. So nitrogen can easily contribute its electron. So here delocalization of electron easily possible because of the less electronegativity of nitrogen. But in case of acid anhydride and ester, there is oxygen that is more electronegative. So these two are less structure 3B and C in both these cases less stable as compared to 3A. By comparing 3B and 3C with each other, in case of ester, R dash group shown here has plus I effect. So it provides electron, it pushes electron toward this positively charged oxygen and it tries to disperse charge on this oxygen. So this structure is most stable, but in case of anhydrides, this group RCOO negative has minus I factor. It withdraws electron towards itself. This overall group tries to withdraw electron towards itself. So it intensifies the positive charge on oxygen. So this structure is even less stable as compared to structure B in case of ester. In case of acid chlorides, no doubt electronegativity of chlorine is almost similar to electronegativity of nitrogen. But in this case, the atomic size difference occurs because in case of chlorine, lone pair is present in 3p orbitals, but carbon has 2p orbital. So overlapping of 3p orbital of chlorine with 2p orbital of carbon is less possible because of the size difference of orbital. So this is least stable in case of acid chlorides. So overall order of stability of this structure 3 is it is more stable in case of amides as compared to esters, that is more stable as compared to acid anhydride, and this is more stable in case of acid chlorides. So least stability of this structure is in case of acid chlorides. So this is the stability order of resonance structure of acid derivatives on the basis of above resonance structures, amides, then esters, then acid anhydrides, and least is the acid chloride. As reactivity is inversely proportional to stability, so reactivity order will be the acid chloride more reactive, then anhydride that are more reactive, then ester that are more reactive, then acid amides. The order of reactivity also explained on the basis of leaving nature of leaving group. Stronger the base, poor is the leaving group. The relative basicity order of these leaving group is NH2 negative. Easily basicity order of NH2 negative is greater than RO negative, that is greater than RCO negative, and it is further more than Cl negative. Stronger the base, poor is the leaving group. So this NH2 negative will not easily leave. So reactivity order is acid chloride because Cl group easily leaves as compared to anhydride that is more reactive than ester, that is further more reactive than acid amides. Next comes acid catalysis of nucleophilic style substitution, means reaction in the presence of acidic conditions. In presence of acid, this carbonyl oxygen accepts proton and form this protonated acid derivatives. Because of this protonation, this oxygen acquires positive charge and attack of nucleophile is more easily as compared to in absence of acidic condition. After attack of nucleophile, this transition state can be represented here. Bond of nucleophile with carbon starts form, and this double bond between carbon and oxygen starts breaking, and this leads to formation of tetrahedral intermediate, followed by removal of this L group, and we get this type of compound, but it is still protonated. Then when by loss of proton we get substitution products. The next topic is interconversions of acid derivatives by nucleophilic acyl substitution. Due to large difference in the reactivity of acid derivatives toward these reactions, it is possible to convert a more reactive acid derivative into less reactive acid derivatives. As we already know the reactivity order, acid chloride is more reactive, so it can be converted into acid anhydrides, or it may be converted into esters and amides. But as anhydrides are less reactive than chloride, so anhydrides cannot be converted into acid chloride, but they can be converted into esters and amides. Further, esters are less reactive than these chlorides and anhydride, so esters cannot be converted into acid chlorides, and since they are more reactive, they can be converted into acid amides. And amides are least reactive, so they cannot be converted into any of the acid derivatives. So amides cannot be converted into any of these acid derivatives. Thank you.